For our last example on related rates problems, a boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, we have an interesting problem. It says here that you have a rope, no, attached to the bow of the boat, okay, where the rope is attached here to the pulley on the dock, okay, and it says that the dock is 1 meter higher than the bow, meaning if you draw a line here, okay, horizontal line, then the distance, okay, of this pulley, no, from that horizontal line is equal to 1 meters. So this is what we mean by this statement, that the bow of the boat, the pulley, no, is 1 meter higher than the bow of the boat. Okay. Now, if the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay. We can actually use this diagram to obtain a working expression, no, for this problem, right? Okay. So what I did here was to draw a horizontal line from the bow of the boat, okay, and draw a line, another line, no, from the pulley down to the horizontal line, okay, so that that line is perpendicular to the horizontal line. And you actually have here a right triangle, okay? Now, to help us analyze this problem, let's use some variables, okay? Let's say that this side, no, of the right triangle formed is x, this side here is y, and this side here is r. That corresponds to the rope, actually, okay? And obviously, because this is a right triangle, then the Pythagorean theorem can be used, no, in this case. Okay, but first let us identify the given values from this problem. So we have here a boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow of the boat. Okay, we have a given value here. The distance from the pulley to the horizontal line, okay, is equal to 1 meter. And since that's denoted by y, then we have, for our first given, y equals 1 meter. Okay. Further, we have, if the rope is pulled in at a rate of 1 meter per second, okay, the rope is pulled in at a rate of 1 meter per second. That talks about a certain quantity that changes, no, with respect to time. What quantity is that? That quantity is, since that refers to the rope, no, that is pulled in, that refers to your r. Okay, so that means that this can be denoted by dr dt equals 1 meter per second, right? Okay, dr dt equals 1 meter per second. Then how fast is the boat approaching the dock when it is 8 meters from the dock. We have another given here. The given actually is 8 meters. That refers to what? That refers to your x, no? Because it says how fast is the boat. The boat is approaching here. Okay, so it's actually traveling a horizontal distance. Okay, approaching the dock. So that refers to the x. And when it says how fast is the boat approaching the dock, that's what we're looking for. That refers to the change of what quantity with respect to time? The change of your x, right, with respect to time. So we have here dx dt when it is 8 meters from the dock, meaning your starting distance is 8 meters. So that's another given, okay, 8 meters. Okay, so let's obtain a working expression from this relationship, from this diagram. This diagram suggests that we have x squared plus y squared equals r squared, right? Using the Pythagorean theorem, okay? And you will notice here that y is actually a fixed value, meaning even if your x changes with respect to time and your r changes with respect to time because you are pulling the rope, right? You're pulling the boat with the rope attached to it. So this is changing. And then the distance also of the boat is changing, okay, as the boat approaches the dock. But your y remains the same, right? So this is fixed. So that means that we can substitute y here. You will have x squared plus 1 squared equals r squared, right? Okay. And then solving, maybe it would help if we isolate the x squared on this side. So we have x squared equals r squared minus 1. Okay. So we have here a working equation. Okay. The reason why we're not substituting 8 meters yet, no, for x is that x is not a fixed value. Okay. 8 is only a starting point. That's the starting distance, but it's not a fixed value because as you are pulling the rope, your x changes, okay, with respect to time. So what we're going to do here is to differentiate both sides with respect to time, okay? So you have d dt x squared equals d dt of r squared minus 1. And then the derivative of x squared with respect to time. X and r are functions of time. So using the chain rule or the implicit differentiation, this is 2x dx dt, right? While r squared, the derivative of that with respect to time is 2r dr dt, and the derivative of 1 is equal to 0. So that's why we have this expression, okay? Now, the next thing to do here is to substitute the given quantities, okay? Your x is given here to be 8, okay? And then the dx dt, well, we're looking for that, right? Okay, dx dt, that's what we're looking for, okay? So 2 times 8 meters equal to 2 times r. Okay, the problem here is we don't have r, okay? If we put r here, then that will leave us two quantities that are unknown. But is there a way to find for the value of r? By the way, your dr dt is given here to be 1 meter per second. So how do you find that r? We need to find this, no? because if we don't know this, then we cannot find the dx dt, which is our main objective. Well, take note that you have a right triangle and your x is given to be 8 meters. Your y is equal to 1 meter. So using Pythagorean theorem, we can easily find the r. So from this expression, we find the value of r. X is 8 meters, so you have 8 squared equals r squared minus 1. Okay, and then this means that your r squared is equal to 64 plus 1, and your r, getting the square root of both sides, is square root of 65. Okay, so we plug this in to this question mark, okay? And the expression now will become 16 meters. This is 2 times 8. The x dt equals 2 times, okay? That r there is square root of 65 meters times 1 meter per second, okay? And then this meter and meter here will cancel, not cancel. It's meter times meter is meter squared. Then you have here 16 meters. We're solving for the x dt, so that means that we divide both sides by 16 meters. Okay, and we obtain multiplying this now, and 1 meter per second. So we have 2 times 65, square root of 65 meters squared per second. And then we should get rid of the 16 meters. So we divide both sides by 16 meters. That's why we have dx dt equals 2 times square root of 65 meters squared per second over 16 meters. Of course, the meter here will cancel, so we're left with meter per second na lang. And then this can be written as square root of 65 over 8 meter per second. Or you can use your calculator to get the approximate value, no, of your dx dt. So you can have 1.01 meter per second. So what is the implication of this? It means that as the rope is pulled at a rate of 1 meter per second, the boat is approaching the dock at a rate of 1.01 meter per second. Okay, so that's the application of that. Okay, so thank you, and God bless everyone. Enjoy watching.